So now let's look at the definitions of the derivatives. So let's look at graph first. So this is the graph y equals f of x. Okay, and if we know this point is given by x and f of x. So this is the x, f of x, and we know there is a tangent line. There is a tangent line, y equals Lx, right? Yeah, this is a tangent line. We just say it's the tangent line. And we know the slope for the tangent line, which is f prime of x, right? For this tangent line. So if we change x a little bit by delta x, so we change x by delta x. So here is delta x. So this would be fx plus delta x. So the question is, so this is corresponding to this one, right? This point. The question is, what about the y values change from here to here, right? From here to here. This is the f of x plus delta x. So we denote this part by delta f of f, which is given by f of x plus delta x minus f of x, right? So the difference between these 2 points would be the y value change from here, from this point to this point. But if we want to use this tangent line to approximate this y change, what's that? Okay, so now let's look at this part. So let's draw this is the x plus delta x, and let's draw a horizontal line here. So you can see this is a right triangle, right? This is a right triangle. This is a right triangle. What is the tangent if this is theta? What is the tangent theta? The tangent theta is the opposite of the adjacent, right? And we also know in the pre-calculus, the slope of this straight line is the tangent theta, right? So the tangent theta is f prime of x. So if you multiply by delta x, this is delta x, right? This is delta x. If you multiply by delta x, which would be this part would be the tangent theta, f prime of x, times delta x. Okay, so we can use this number to approximate this part. To approximate this part, I use other color. To approximate this part, this is the change, actual change, right? To approximate this part. And this is the approximation. This is the approximation, right? So if delta x is small, so you can see the purple line and the origin line would be very close to each other, right? So this delta f, which is the actual change, the true change, okay, this true change can be approximated by f prime x dx times delta x, times delta x. So here, if we let dx to be delta x, we use another notation. That means why we use dx. Dx is represent a small change, right? Delta x is just a change in x, but dx represent a small change in x. So that means we can use this approximation. This will give you a good approximation when delta x is small. So in other words, this delta f, this is the true change, can be approximated by f prime of x times dx, right? So here, let's define the right side. We give a right side a name, or let's define the right side dy, a name which is called dy. dy is equal to f prime of x dx. So this dy is the vertical change in the tangent line with respect to the horizontal change dx. Okay, so this dy is the vertical change, in the tangent line with respect to the horizontal change horizontal small change dx. Okay, we give a name dy and dx. dy is called the differential of y, and the dx is called the differential of x. So our true change delta f can be approximated by the dy. Right. So here, so this is we will not care about the further application for this formula, but we are interested in this definition, dy equals f prime of x dx. Okay, so how to remember that? So here the remark, how to remember that? So this is if we let y equals f prime of x, right? What is dy of y equals f of x. What is dy over dx? dy over dx, which is f prime of x, right? So if you treat why we use this notation, this is called the Leibniz notation. You should be very familiar with this one. We use this one a lot, right? We use the Leibniz notation. The good thing to use Leibniz notation is you can treat this one as a fraction, right? You can treat this one as a fraction. Then you multiply dx on both sides. Then you will have dy equals f prime of x dx, right? So it's very easy to memorize it, right? You just start from the derivative and multiply dx on both sides. So now let's look at one example. If f of x, y equals, if y equals x squared, okay. If y equals x squared, what is the differential of y? So this would be, so you take the derivative, which is equal to 2x, right? Then you multiply the x on both sides, so dy equals 2x dx. So this is one example. Another example, y equals f of x. What is f of x? F of x is given by x squared plus 2 to the square. So dy over dx is equal to f prime of x, right? F prime of x equals, we need to do the calculation for the derivative. For this one, this is the outside function is the square power, so it's the 2 to the 2 minus 1. So what is inside? The inside would be x squared plus 2. We keep the inside, then times the derivative of the inside function. So if you do the calculation, it would be, this would be 2x, so times 2 would be 4x. This is x squared plus 2. Okay, so this is the dy over dx equals this one. What is dy? dy is equal to 4x x squared plus 2 dx. So it's very easy to find the differential y, right? You just need to take the derivative first, then multiply both sides by dx. You will get this result quickly.